Chapter number 1. Sets, Relations and Functions. Dear friends, first let us learn about sets. A collection of well-defined objects is called a set, and the object in it is called its element or member. There are two methods of representing a set. First one is roster or tabular or list method, and the second one is set builder or ruler method. The example of roster method is A is equal to into brace brackets 10, 20, 30, 40, 50, bracket close. This can be read as A is a set of 10, 20, 30, 40 and 50. That is, here we write the elements of a set as a series of numbers. The example of set builder method, P is equal to into brace brackets X vertical line X equal to 10n, comma, n belongs to n, that is natural numbers, comma, n less than or equal to 5, bracket close. This can be read as P is a set of X where X is equal to 10n, n belongs to n, that is natural numbers, and n is less than or equal to 5. That is, here we define variable x in terms of natural number n instead of writing a series of numbers.
Types of sets. Number 1. Empty set. Now, an empty set is which does not contain any element. That is called empty set or null set or void set. For example, number 1. Set of all prime numbers between 89 and 97. Number 2. Set of all x for all x belonging to natural numbers where x is greater than 2 but less than 3. Number 3. The set of all real numbers whose square is negative. This empty set is denoted by phi or two curly brackets. Note that the sets 0 and phi are not empty sets as they contain one element, namely 0 and phi respectively. Number 2. Singleton set. A set which contains only one element is called singleton set. For example, set of 2 is a singleton set. The set A is equal to set of all integers which are neither positive nor negative is the singleton since A is set of 0. Number 3. Finite and infinite set. A set containing a finite numbers of elements is called a finite set. Thus, in a finite set, one can count the elements. For example, set of all the vowels in English alphabet, set of all students in a class. A set which is not finite is called an infinite set. N, I, Q, R are all infinite sets. Number 4. Subset. If every element of a set A is also an element of set B, then A is said to be subset of B. We write this as A is subset of B like this. A is subset of B if and only if X belongs to A implies X belongs to B. It is clear from this definition that every set is a subset of itself. That is, for any set A is subset of A. For example, if A is set of 1, 2, 3, 4 and B is set of 1, 2, 3, 4, 5, 6, then A is subset of B. Next example, if X is equal to set of all X, for X is a letter in the word wolf. Y is equal to set of all X, for X is a letter in the word follow. Then X is equal to set of W, O, L, F, and Y contains the letters F, O, L, L, O, W. But O and L are repeated. So Y is set of F, O, L, W. Equal sets. Two sets A and B are said to be equal if and only if A is subset of B and B is subset of A. It is denoted by A is equal to B. If A and B are not equal, we write it like this. Remark. If A is not a subset of B, then we write this as A is not a subset of B or like this. Clearly, in this case, set A contains at least one element which is not in the set B. For example, let A is equal to set of 1, 3, 5 and B is equal to set of 2, 3, 4, 5, 6. Then 1 belongs to A, but 1 does not belong to B. Hence, A is not the subset of B. Thus, A is not the subset of B if there exists X belong to A and X does not belong to B. Note, empty set is a subset of every set. That is, phi is subset of A for any set A. Now, every set is the subset of itself. That is, A is subset of A for every set A. Now, proper subset. If all the elements of the set A are in the set B and B contains at least one element which is not in A, we say that A is proper subset of B. We write it as like this. Thus, A is proper subset of B if A is subset of B but A is not equal to B. For example, if A is equal to set of 1, 3, 5 and B is equal to set of 1, 2, 3, 4, 5, 6, then A is proper subset of B. In usual notation, N is proper subset of I, which is proper subset of Q, and Q is proper subset of R. Universal set. A set X is said to be a universal set if all the sets under consideration are subsets of the set X. The universal set is sometimes denoted by U. For example, if A is set of 1, 2, 3, 4, 5, 6, B is set of 1, 2, 3, 4, so on up to 50, and C is set of 2, 4, 6, so on up to 100, are sets under consideration, then we take the set n of all natural numbers as the universal set. Note, the set I of integers can also be a universal set for the above example. Hence, a universal set has to be clearly prescribed. Now we have Venn diagrams. A set can be represented by a closed geometrical figure like a circle, a triangle, a rectangle, etc. Such a presentation of the set is called the Venn diagram. The points inside the figure represent member of the set. Some Venn diagrams are as follows.
Now let us learn the operations on sets. Complement of a set. If A is subset of universal set U, then the set of element in U but not in A is called the complement of the set and is denoted by A dash or A complement. For example, U is equal to 1, 2, 3, 4, 5. A is equal to 1, 2, 4. Then A dash is equal to 3, 5. Union of sets. If A and B are two sets, then union of sets A and B is set of all elements which are in A or B. For example, A is equal to 1, 2. B is equal to 3, 4. U is equal to 1, 2, 3, 4, 5. Then A union B is equal to 1, 2, 3, 4. Here you can see in the figure that 1, 2, 3, 4 lie in A and B respectively. Intersection of sets. The intersection of two sets A and B is the set of all elements which are both in A and B. A is equal to 1, 2, 4. B is equal to 2, 3, 5. Then the shaded portion shows A intersection B, that equals to 2. Here 2 lies in the region common to A and B. Disjoint sets. Two sets A and B are said to be disjoint if they have no common element. So A intersection B is equal to null set. Difference of sets. The difference of set A and B is the set of elements which are in A but not in B. So A minus B is equal to A intersection B dash. B minus A is equal to A dash intersection B. For example, let A is equal to 1, 2, 4. B is equal to 1, 3, 7. Therefore, A minus B is equal to 2, 4. And B minus A is equal to 3, 7.
Exercise 1.1. Question number 1. Describe the following sets in roster form. Number 1. Set of all X such that X is a letter or word marriage. Solution. Let A is equal to set of all X such that X is the letter or word marriage. Therefore, A is equal to set of M, A, R, I, G, E.
Exercise 1.1. Describe the following sets in roster form. Number 2. Set of X where X is an integer. Minus 1 upon 2 is less than X and X is less than 9 upon 2. Answer. In the roster form, let the set be A. Therefore, A is equal to into brace brackets 0, 2 upon 2, 4 upon 2, 6 upon 2, 8 upon 2, bracket closed. Therefore, A is equal to into brace brackets 0, 1, 2, 3, 4, bracket closed. Please note 1 upon 2, 3 upon 2 and 7 upon 2 are not considered as they are not integers.
Number 3. Set of X such that X is equal to 2n, X belongs to n belongs to n. Solution. Let C is equal to set of all X is equal to 2n, X belongs to n belongs to n. Therefore, C is equal to set of 2, 4, 6, 8 and so on. Question number 2. Describe the following sets in set builder form. Number 1. Set of 0. Solution. Let A is equal to set of 0. Now 0 is an integer lying between -1 and 1. Therefore, A can be written in set builder form as A is equal to set of all X such that X belongs to Z, X is greater than -1 but less than 1. Or 0 is a whole number but it is not a natural number. Therefore, A can also be written in set builder form as A is equal to set of all X, X belongs to whole number, X does not belong to natural number. Number 2. Set of 0 plus -1 plus -2 plus -3. Solution. Let B is equal to set of 0 plus -1 plus -2 plus -3. Well, B is the set of integers from -3 to 3. Therefore, B can be written in set builder form as B is equal to set of all X such as X belongs to Z, where X is greater than or equal to -3 but less than or equal to 3.
Question number 2. Describe the following sets in set builder form. Number 3. Into brace brackets 1 upon 2, 2 upon 5, comma 3 upon 10, comma 4 upon 17, comma 5 upon 26, comma 6 upon 37, comma 7 upon 50, bracket close. Answer. Let B is equal to into brace brackets 1 upon 2, comma 2 upon 5, comma 3 upon 10, comma 4 upon 17, comma 5 upon 26, comma 6 upon 37, comma 7 upon 50, bracket closed. By analyzing, we can say that denominator of each term is equal to numerator square plus 1, such as 2 is equal to 1 square plus 1, 5 is equal to 2 square plus 1, 10 is equal to 3 square plus 1, etc. Therefore, in set builder form, B is a set of all x such that x is equal to n upon n square plus 1, where n belongs to natural numbers and n is less than or equal to 7, bracket closed. We can verify it as if x is equal to 1, b is equal to 1 upon 1 square plus 1, that equals to 1 upon 1 plus 1, that equals to 1 upon 2. If x is equal to 2, b is equal to 2 upon 2 square plus 1, that equals to 2 upon 4 plus 1, that equals to 2 upon 5, and so on.
Question number 3. If A is equal to set of all x such that 6x squared plus x minus 15 is equal to 0, B is equal to set of all x such that 2x squared minus 5x minus 3 is equal to 0, C is equal to set of all x such that 2x squared minus x minus 3 is equal to 0. Find number 1, A union B union C. Solution. A is equal to set of x such that 6x squared plus x minus 15 is equal to 0 is the set of solutions. That is, the solution set of the equation 6x squared plus x minus 15 is equal to 0. Hence, we solve this equation 6x squared plus x minus 15 is equal to 0. If you split it, it is 6x squared plus 10x minus 9x minus 15 is equal to 0, which means 2x into 3x plus 5 minus 3 into 3x plus 5 is equal to 0. Therefore, 3x plus 5 into 2x minus 3 is equal to 0. So, either 3x plus 5 is equal to 0 or 2x minus 3 is equal to 0. So, x is minus 5 upon 3 or x is 3 upon 2. Therefore, the solution set of the equation 6x squared plus x minus 15 is equal to 0 is A is equal to set of minus 5 upon 3, 3 upon 2. Similarly, solving the equation 2x squared minus 5x minus 3 is equal to 0 and 2x squared minus x minus 3 is equal to 0, we have B is equal to set of minus 1 upon 2, 3, and C is equal to set of 3 upon 2, minus 1. Now, number 1. A union B union C. It will be set of minus 5 upon 3, 3 upon 2, union set of minus 1 upon 2, 3, union set of 3 upon 2, minus 1. So it is set of minus 5 upon 3, 3 upon 2, minus 1 upon 2, 3, minus 1, which means it is set of minus 5 upon 3, minus 1, minus 1 upon 2, 3 upon 2, 3. Number 4. If A, B, C are the sets of the letters in the words college, marriage, and luggage respectively, verify that set of A minus B union C is equal to set of A minus B intersection A minus C. Solution. Now A is equal to set of letters of word college. Therefore, A is equal to set of C, O, L, E, G. B is equal to set of letters of word marriage. So B is equal to set of M, A, R, I, G, E. C is equal to set of letters of the word luggage. So C is equal to set of L, U, G, A, E. Now B union C would be set of M, A, R, I, G, E union set of L, U, G, A, E, which means it is set of M, A, R, I, G, E, L, U. Now A minus B union C would be set of C, O, L, E, G minus set of M, A, R, I, G, E, L, U, which means it is set of C, O. Let us put it as 1. Also, A minus B would be set of C, O, L, E, G minus set of M, A, R, I, G, E, which is equal to set of C, O, L. Now A minus C is equal to set of C, O, L, E, G minus set of L, U, G, A, E, which is equal to set of CO. Therefore, A minus B union A minus C is equal to set of COL union set of CO, that is set of CO. Let us put it as 2. Now from 1 and 2 you will see that set of A minus B union C is equal to set of A minus B intersection A minus C. Question number 5. If A is equal to set of 1, 2, 3, 4, B is equal to set of 3, 4, 5, 6, C is equal to set of 4, 5, 6, 7, 8, and universal set X is equal to set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Verify the following. Number 1. A union B intersection C is equal to A union B intersection A union C. Solution. Now, B intersection C would be set of 3, 4, 5, 6 intersection set of 4, 5, 6, 7, 8, that is set of 4, 5, 6. Now A union B intersection C would be set of 1, 2, 3, 4, union, set of 4, 5, 6. That is set of 1, 2, 3, 4, 5, 6. Let us put it as 1. Now A union B would be set of 1, 2, 3, 4, union set of 3, 4, 5, 6, which is set of 1, 2, 3, 4, 5, 6. Well, now A union C would be set of 1, 2, 3, 4, union set of 4, 5, 6, 7, 8, which is set of 1, 2, 3, 4, 5, 6, 7, 8. Therefore, A union B intersection A union C is equal to set of 1, 2, 3, 4, 5, 6, intersection set of 1, 2, 3, 4, 5, 6, 7, 8, which means it is set of 1, 2, 3, 4, 5, 6. Let us put it as 2. Now, from 1 and 2, you can easily make out that A union B intersection C is equal to A union B intersection A union C.
Question number 5. If A is a set of 1, 2, 3, 4, B is a set of 3, 4, 5, 6, C is a set of 4, 5, 6, 7, 8, and a universal set X is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then verify the following. Number 2. A intersection B union C is equal to A intersection B union A intersection C. From the given data, B union C is equal to 3, 4, 5, 6, 7, 8. Therefore, A intersection B union C is equal to 3, 4. That is, the elements common to A and B union C. Let this be equation number 1. Now, A intersection B is equal to 3, 4, and A intersection C is equal to 4. Therefore, A intersection B union A intersection C is equal to 3, 4. Let this be equation number 2. Therefore, from equations 1 and 2, A intersection B union C is equal to A intersection B union A intersection C. Hence proved.
Number 3. Complement of A union B is equal to A complement intersection B complement. Solution. Now first let us find A union B. A union B is equal to set of 1, 2, 3, 4, union set of 3, 4, 5, 6, which is equal to set of 1, 2, 3, 4, 5, 6. Therefore, complement of A union B would be set of 7, 8, 9, 10. Let us put it as 1. Now A complement would be equal to set of 5, 6, 7, 8, 9, 10. And B complement would be equal to set of 1, 2, 7, 8, 9, 10. Now A complement intersection B complement will be set of 5, 6, 7, 8, 9, 10 intersection set of 1, 2, 7, 8, 9, 10, which is equal to set of 7, 8, 9, 10. Now from 1 and 2 we get complement of A union B is equal to A complement intersection B complement. Number 4. Complement of A intersection B is equal to A complement union B complement. Solution. Now here first we'll find A intersection B. That would be set of 1, 2, 3, 4 intersection set of 3, 4, 5, 6. That is set of 3, 4. Now complement of A intersection B is equal to set of 1, 2, 5, 6, 7, 8, 9, 10. Let us put it as 1. Now A complement is equal to set of 5, 6, 7, 8, 9, 10 and B complement is equal to set of 1, 2, 7, 8, 9, 10. Now here A complement union B complement will be set of 5, 6, 7, 8, 9, 10 union set of 1, 2, 7, 8, 9, 10 which is equal to set of 1, 2, 5, 6, 7, 8, 9, 10. Let us put it as 2. If you notice 1 and 2, you'll find that complement of A intersection B is equal to A complement union B complement.
Number 5. A is equal to A intersection B union A intersection B dash. Answer. From the given data, x is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A is equal to 1, 2, 3, 4. Let this be equation number 1. B is equal to 3, 4, 5, 6. Therefore, B dash is equal to 1, 2, 7, 8, 9, 10. Therefore, A intersection B dash is equal to 1, 2. And A intersection B is equal to 3, 4. Therefore, A intersection B union A intersection B dash is equal to 1, 2, 3, 4. Let this be equation number 2. From equations 1 and 2, A is equal to A intersection B union A intersection B dash. Hence proved.
Number 6. B is equal to A intersection B union A complement intersection B. Solution. Now B is equal to set of 3, 4, 5, 6. Let us put it as 1. A intersection B is equal to set of 1, 2, 3, 4 intersection set of 3, 4, 5, 6. That is set of 3, 4. And A complement is equal to set of 5, 6, 7, 8, 9, 10. Therefore, A complement intersection B is equal to set of 5, 6, 7, 8, 9, 10. Intersection set of 3, 4, 5, 6. That is set of 5, 6. Therefore, A intersection B union A complement intersection B is equal to set of 3, 4 union set of 5, 6. That is set of 3, 4, 5, 6. Let us put it as 2. Now from 1 and 2 we get B is equal to A intersection B union A complement intersection B. Number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. Solution. Now A is equal to set of 1, 2, 3, 4 and B is equal to set of 3, 4, 5, 6. Which means number of elements in A is equal to 4 and number of elements in B is equal to 4. Now, A union B is equal to set of 1, 2, 3, 4 union set of 3, 4, 5, 6. That is set of 1, 2, 3, 4, 5, 6. And A intersection B is equal to set of 1, 2, 3, 4 intersection set of 3, 4, 5, 6. That is set of 3, 4. Now number of elements in A union B is equal to 6 and number of elements in A intersection B is equal to 2. Therefore, number of elements in A plus number of elements in B minus number of elements in A intersection B would be equal to 4 plus 4 minus 2, that is 6. If you notice, it is equal to number of elements in A union B. Hence, number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. Question number 6. If A and B are subsets of the universal set X and number of elements in X is equal to 50, number of elements in A is equal to 35, number of elements in B is equal to 20, number of elements in A complement intersection B complement is equal to 5, find number 1, number of elements in A union B. Solution. Now number of elements in X is equal to 50 and number of elements in A complement intersection B complement is 5. Since A complement intersection B complement is equal to the complement of A union B, therefore the number of elements in the complement of A union B is equal to number of elements in A complement intersection B complement, that is 5. So number of elements in A union B is equal to number of elements in X minus number of elements in complement of A union B. That is 50 minus 5, which is 45. Number 2. Number of elements in A intersection B. Well, number of elements in A intersection B is equal to number of elements in A plus number of elements in B minus number of elements in A union B. So it is 35 plus 20 minus 45, which is 55 minus 45, so it is 10. So number of elements in A intersection B is 10. Number 3. Number of elements in A complement intersection B. Now number of elements in A complement intersection B is equal to number of element in B, number of element in A intersection B. So it is 20 minus 10, that is 10. Number 4. Number of element in A intersection B complement. Now number of element in A intersection B complement would be equal to number of element in A minus number of element in A intersection B. That is 35 minus 10, so the answer is 25. Question number 7. In a class of 200 students who appeared in a certain examination, 35 students failed in MHT CET, 40 in AIEEE, 40 in IIT entrance, 20 failed in MHT CET and AIEEE, 17 in AIEEE and IIT entrance, 15 in MHT CET and IIT entrance, and 5 failed in all 3 examinations. Find how many students, number 1, did not fail in any examination. Solution. Let X set of all students, M set of students failed in MHT CET, A as set of students failed in AIEEE, I as set of students failed in IIT entrance. We are given the following. Number of elements in X is 200. Number of elements in M is 35. Number of elements in A is 40. Number of elements in I is 40. Number of elements in M intersection A is 20. Number of elements in A intersection I is 17. Number of elements in M intersection I is 15. Number of elements in M intersection A intersection I is 5. Now the Venn diagram is shown as follows. Number 1. The number of students who did not fail in any examination would be number of elements in the complement of M union A union I, which is equal to number of elements in X minus number of elements in M union A union I, that is 200 minus 5 plus 15 plus 8 plus 10 plus 5 plus 12 plus 13, which is 200 minus 68, and that is 132. Number 2. Failed in AIEEE or IIT entrance. Solution. The number of students who failed in AIEEE or IIT entrance would be number of elements in A union I. So it is 15 plus 8 plus 10 plus 5 plus 12 plus 13, that is 63. So number of students who failed in AIEEE or IIT entrance are 63.
Question number 8. From amongst 2000 literate individuals of a town, 70% read Marathi newspapers, 50% read English newspapers, and 32.5% read both Marathi and English newspapers. Find the number of individuals who read 1. At least one of the newspapers, 2. Neither Marathi nor English newspaper, and 3. Only one of the newspapers. Answer. Total literates L is equal to 2000. Number of literates who read Marathi newspapers, M is equal to 70% of 2000, that equals to 70 upon 100 into 2000, that equals to 1400. Number of literates who read English newspapers, E, is equal to 50% of 2000, that equals to 50 upon 100 into 2000, that equals to 1000. Number of literates who read both the newspapers, B, is equal to 32.5% of 2000, that equals to 32.5 upon 100 into 2000, that equals to 650. This can be represented using Venn diagram in this way. L represents total literates, M represents literates who read Marathi newspapers, E represents literates who read English newspapers, and B represents literates who read both the newspapers. Therefore, N of L is equal to 2000, N of M is equal to 1400, N of E is equal to 1000, and N of B is equal to 650. Number 1. Let N of O be the number of readers reading at least one of the newspapers. Now, N of M dash, that is, readers not reading Marathi newspapers, is equal to N of L minus N of M, that equals to 2000 minus 1400, that equals to 600. N of E dash, that is, readers not reading English newspapers, is equal to N of L minus N of E, that equals to 2000 minus 1000, that equals to 1000. N of B dash, that is, readers not reading any newspaper, is equal to N of L minus N of B, that equals to 2000 minus 650, that equals to 1350. Therefore, N of O is equal to N of L minus N of M dash, that is, readers not reading Marathi newspapers, minus N of E dash, that is, readers not reading English newspapers, plus N of B dash, that is, readers not reading any newspaper, that equals to 2000 minus 600 minus 1000 plus 1350, that equals to 1750. So the answer is the number of literates who read at least one newspaper is 1750. 2. Neither Marathi nor English newspapers. Let n of A be the number of readers for the given condition. Therefore, n of A is equal to n of L minus n of O, that equals to 2000 minus 1750 as derived in 1, that equals to 250. Therefore, 250 individuals read neither Marathi nor English newspapers. 3. Only one of the newspapers. Let n of B be the number of readers for the given condition. Number of readers reading only Marathi newspaper is equal to n of M minus n of B is equal to 1400 minus 650, that equals to 750, and number of readers reading only English newspapers is equal to n of E minus n of B is equal to 1000 minus 650, that equals to 350. Therefore, n of B is equal to 750 plus 350, that equals to 1100. Therefore, 1100 individuals read only one of the newspapers.
Question number 9. In a hostel, 25 students take tea, 20 students take coffee, 15 students take milk, 10 students take both tea and coffee, 8 students take both milk and coffee, none of them take tea and milk both, and everyone takes at least one beverage. Find the number of students in the hostel. Solution. Let T be set of students who take tea, C set of students who take coffee, M set of students who take milk. We are given the following. Number of T is equal to 25. Number of C would be 20. Number of M is 15. Number of T intersection C is equal to 10. Number of M intersection C is equal to 8. Number of T intersection M is equal to 0. Now the Venn diagram is shown as follows. From the Venn diagram, number of students in the hostel would be number of T union C union M. That means it is 15 plus 10 plus 2 plus 8 plus 7, which is equal to 42. Question number 10. There are 260 persons with a skin disorder. If 150 had been exposed to the chemical A, 74 to the chemical B, and 36 to both chemical A and B, find the number of persons exposed to number 1. Chemical A but not chemical B. Solution. Let X be set of all persons. A is set of persons exposed to chemical A. B would be set of persons exposed to chemical B. We are given the following. The number of X is equal to 260. Number of A is 150. Number of B is 74. And number of A intersection B is 36. The Venn diagram is shown as follows. Now from the Venn diagram, number 1, number of persons exposed to chemical A but not chemical B would be number of A intersection B, that is 114. Number 2, chemical B but not chemical A. That would be number of persons exposed to chemical B but not chemical A. That is number of A composite intersection B. That is 38. Now number 3. Chemical A or chemical B, which means number of persons exposed to chemical A or chemical B, that will be equal to number of A union B, that is 114 plus 36 plus 38, which is 188.
Question number 11. If A is the set of 1, 2, 3, write down all possible subsets of A, that is power set of A. Answer. We know that null set is a subset of every set. The other subsets could be the set containing 1, set containing 2, set containing 3, set containing 1, 2, set containing 1, 3, set containing 2, 3, and set containing 1, 2, 3. Therefore, power set of A is equal to set containing these sets, null set, set of 1, set of 2, set of 3, set of 1, 2, set of 1, 3, set of 2, 3, and set of 1, 2, 3.
Question number 12. Write the following intervals in set builder form. Number 1. Minus 3, 0. Solution. We have minus 3, 0, which is equal to set of all x such that x belongs to rational number where x is greater than minus 3 but less than 0. Number 2. 6, 12. Well, 6, 12 is equal to set of all x where x belongs to rational number, x is greater than or equal to 6 but less than or equal to 12. Number 3. 6, 12. Well, here 6, 12 is equal to set of all x where x belongs to R, x is greater than 6 but less than or equal to 12. Number 4. Minus 23, 5. Now we have minus 23, 5, which is equal to set of all x where x belongs to R. Now here x is greater than or equal to minus 23 but less than 5. Question number 13. Using Venn diagrams, represent number 1. Complement of A union B. Solution. Well, here is the Venn diagram of complement of A union B. Number 2. A complement union B complement. Well, this is the Venn diagram of A complement union B complement. Number 3. A complement intersection B. Well, here is the Venn diagram of A complement intersection B. Number 4. A intersection B complement. Well, this is the diagram of A intersection B complement.
Definition. Relation. If A and B are two non-empty sets, then only subset of A into B is relation from A to B. If R is a relation and X, Y belong to R, then it is denoted by XRY, where X is the pre-image of Y under R and Y is the image of X under R. For example, let A be the set containing 1, 2, 3, 4, 5 and B be the set containing 1, 4, 5. Let R be a relation such that X, Y belongs to R implies X is less than Y. We list the elements of R. Answer. Therefore, R is the set containing 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. Arrow diagram for this relation R is given by the figure. Domain. The set of all first components of ordered pairs in a relation R. For example, R is a set of 1, 3, 2, 4, 3, 5. Then domain is equal to 1, 2, 3. Range. The set of all second components of ordered pairs in a relation R. For example, R is a set of 1, 4, 3, 7, 4, 4. Then the range of R is equal to 4, 7. Codomain. If R is a relation from A to B, then set B is called the codomain of the relation R. Please note that range is a subset of codomain. Types of relations. A. One-to-one relation. If every element of A has at most one image in B and distinct elements in A have distinct images in B. For example, in the figure, 1 has only one image in B, that is 4, and 1, 2, 3 in A have different images, that is 4, 5, 6 in B. V. Many one relation. If two or more than two elements in A have same image in B, for example, in the figure, 2 and 4 in A have same image, that is 2 in B. C. Into relation. If there exists at least one element in B which has no pre-image in A. For example, in given figure, element 3 in B doesn't have any pre-image in A. D. Onto relation. if every element in B has a pre-image in A. For example, in the given figure, both the elements in B, that is 4 and 8, have pre-image in A, that is 1 and 2 respectively. Binary relation on a set. If A be a non-empty set, then subset of A into A is binary relation on A.